Hi everyone, my name is Anna, and with Jesse, Andrew, and Tom, we are presenting our final project presentation on the steady-state kinematics of maple copter flight with scaling. So first we are going to go through some background information. Maple copters are the seeds from maple trees, as shown in this image here. They have an asymmetrical shape with the center of mass shifted towards one end. The base consists of a single seed, and then a thin, flat, and curved wing-like structure extends from the seed. This design slightly distributes the weight and provides this unique aerodynamic stability when the seeds fall. As the maple copters fall, they spin as they descend. The spinning motion of the seed slows its descent, which increases the time the seed spends in the air and allows it to drift further from the tree. The asymmetric shape causes an uneven drag, making the seed spin in different directions. When analyzing maple copters, there are two important things to look at: the flight phases and the lift. Shown in the image on the right are the different flight phases. The seed starts at an initial position and then descends through a transition phase. As the seed starts to gain speed, the airflow across the wing generates lift and the autorotation begins. The seed then reaches a steady state fall, which is a balance between gravitational forces and aerodynamic lift, which is a very high stability state. Now, how is the autorotation generated? The autorotating seed creates a leading edge vortex. As the maple copter spins, a vortex along the leading edge of its wing, which is shown in the image below, forms. This vortex lowers pressure on top of the wing, which pulls the seed upward and creates a resistance to motion. This slows the seed's descent, and the vortex stays attached to the leading edge, which is what maintains this lift and slow descent. Current research has been performed on maple copters relating to the relationship between seed morphology and dispersal, flow visualization of vortices, and bio-inspired designs. For our project, our team wanted to look more into the autorotation aspect of the maple copters, specifically how different sizes, as shown on the left part of the image, and cuts, as shown on the right part of the image, affect the velocity changes in the autorotation. This allows us to better understand the amount of time until the maple copter reaches steady state.
Next, we'll go over our experiment setup. For the experiment, we are dropping the maple seeds from a height of 17 feet to ensure we achieve the steady state phase of the fall. The seed will drop down past a white backdrop with a ruler used for reference during video post-processing. Our data acquisition system consists of 3 cameras set up to capture different angles and frame rates. Camera 1 will be oriented perpendicular to the backdrop and recording at 240 frames per second. Camera 2 is placed at the top of the backdrop, oriented parallel to it and recording at 240 frames per second as well. And finally, a third camera is set up perpendicular to the backdrop and slightly offset to the right and recording at a standard 30 frames per second for real-time capture of the drops. And to eliminate as much external influence on the drop test as possible, we performed it indoors. With that, I'll move on to the next slide, which has information about the maple seeds or samaras we are testing. For our test, we used a maple seed design found online in 3D printed scaled versions as well as cut versions of the seed. On the bottom left shows the 120% scaled maple seed with a span at 2.25 inches. To the right of that is a 3D rendering of the seed, and that was manipulated and 3D printed out of ABS to produce the different scaled and cut versions you see to the right. Only the 120% scaled seed with a 2.25 inch span was cut for our testing. The next slide shows an example of the footage captured from one of our drop tests. Camera 1 shows us the slow motion footage of the maple seed spinning as it descends. Camera 2 shows a top view which lets us capture rotation of the seed. And camera 3, as stated before, shows the drop in real time.
Now we will go through the results of our experiments. So what we noticed qualitatively in our experiments is that cut seeds reliably reach autorotation. And we cut seeds up to 25.4%, and all of those seeds reach autorotation, like this one here. We can't say that seeds larger than that will reach autorotation because they weren't tested, but we can say for up to 25.4%. We also noticed that autorotation does not occur for seeds that are too large. So seeds that were scaled 80% up from the reference seed were able to reach autorotation, but larger seeds were not. The conclusions, first we have to note that autorotation is a balance between moment, angle, and angular velocity. So for a gyroscopic wheel here, we see that there's a moment, that the wheel spins at an angle, and at a given angular velocity. And all these three values effectively balance out to create a gyroscopic motion. This might be harder for a larger seed though, because it has a larger resistance to rotate, larger moment of inertia, and a gravitational force. So as previously mentioned, the larger mass will likely introduce a large moment of inertia, so the autorotation will have to effectively work harder to auto-rotate, or the conditions have to be more extreme in order for it to auto-rotate to overcome the moment of inertia. And the lift force also seems to be much smaller than the inertial force, so a high Reynolds number. And what this means is effectively that we have the gravitational force much larger than the lift force, and it should or will likely fall like a brick and just not have time for it to auto-rotate. The leading edge vortex also, we have concluded it causes auto-rotation. So if you see here, we have a leading edge vortex, a winged tip vortex, and a winged root vortex. For a cut seed, the leading edge is the same and is identical between its uncut version and its cut version, but the trailing edge is different. So we can conclude that the leading edge vortex for both cases will be the same, but the wing tip and wing root vortices will not be the same. And because both the cut and uncut version of the seeds both reach autorotation, we can conclude that the leading edge vortex introduces the most lift to the system, which is what introduces the autorotation, and it interacts with the seed most dominantly. However, we can also likely, and what we will look at in the following slides, is that these other vortices, though, might have other niche impacts that we want to analyze. So what we have on the left-hand side is the seed that is scaled up by 90%. And on the right-hand side, we have the seed that is scaled up by 20%. So seed that is scaled up by 20%, we can see it rotating from the very top, and we can also see it reach a steady state around this point here. And we notice that it just falls down much slower and just elegantly and effectively, it is close to parallel to the ground when it is falling. And this rotating motion allows it to not become perpendicular to the ground. The seed will naturally, without a rotating motion, want to just fall straight perpendicular to the ground. If that's where the total torque on the system would be zero, but this rotation prevents that. Meanwhile, for the larger seed, as we previously mentioned, it has a larger moment of inertia, so it wants to resist the rotating motion. That allows it to fall down more parallel to the ground. In addition, the gravitational force is much larger than the lift force, so it also falls down much quicker. And we see here that as predicted, or as previously explained, it falls down like a brick. And it's actually very funny sometimes just to notice that this small increase in surface area and size will change the dynamics of the flight very drastically. On this graph, we plot the velocity versus time for different seeds. So we have the reference seed, scaling of 20% up and a scaling of 60% up. We didn't include the other seeds because they had a lot of noise in the data due to the very few time steps that our software was able to analyze for. But what we notice is that the smaller seeds reach steady state faster. So we can see here for the reference seed, we're at a maximum effectively when we start recording. And then we can plausibly conclude that we reach some sort of steady state. These points aren't in a straight line, but with the errors that our recording has, we can conclude that it's likely a steady state. We see for the 20% increase seed, we see it increase and then decrease, and these last 3 points are reliably a steady state. And with the largest seed, we see so much instability that we can't really tell where the maximum is and where it starts becoming steady state. I would, judging by the pattern of the maximum before steady state, so this point here and this point here, shifting to the right, we can assume that this is the maximum and that it will then go to a steady state out into the future. The reason for this is that for the smaller seas, the inertial forces are comparable to the viscous forces, and there's higher viscous dampening effects. For the cut seeds, so we have the blue seed is our reference seed that's uncut, and we see that for the cut seeds, the pattern is slightly different. We have the maximum at the same point for all the cut seeds, which is interesting to notice that they have the same behavior and that it occurs at the same time as the reference seed. But what we also notice is that while the reference seed goes to a steady state, the cut seeds have more noise in the data and do not reach a steady state as reliably or as quickly as the reference seed. So on the left-hand side, we have published data or literature data on the simulations of a maple seed. And we see that this maximum that we have here corresponds to this point here on the descending velocity. And after this point, we decrease and reach a steady state. And this is the pattern that we see for the reference seed. And as again mentioned as before, while we do see the maximum for the cut seeds, we do not see it settle into a steady state after that. And the hypothesis for this is that while we do still have a leading edge vortex, the wing root vortices and the wingtip vortices might be fairly different due to essentially the cut trailing edge of the cut seeds. And yeah, so the conclusion is that these wingtip vortices and these wing root vortices introduce stability to the maple seed and are what contributes to it reaching a steady state. So if we observe the flight for the two seeds, what we notice is that for the reference seed, effectively after this point here, the reference seed falls at a constant angle to the ground, or even close to parallel to the ground, and that angle is not changing on its flight down and has reached a steady state. What we notice for the cut seed, though, is that it is parallel to the ground from this point here for a tiny bit, but once it reaches this point here, it is not parallel to the ground. So effectively, we have it being parallel to the ground for a short period of time. We think it's reached a steady state, and then the angle changes again, and we realize we're not at a steady state. So effectively, the reference case has a steady and smooth descent downwards. The cut seed has a more unpredictable path downwards. What we also plot is the number of rotations during the flight to the dimensionless area. So this is the area that we currently have divided by the surface area of the reference case. And what we notice is that when we cut the seed slightly, we actually increase the total number of rotations. But then after we keep cutting the seed, we start decreasing more and more. So what we notice is that a slight cut in the seed will increase the angular velocity of the seed, but cutting it more and more will actually start decreasing it back again. We do not know the exact reasoning of this, but this is an interesting observation we made. So what we notice is that large seeds are harder to reach autorotation and smaller seeds reach autorotation quicker. This is effectively because a larger seed has a larger moment of inertia, so it's more resistant to rotation. And in addition, its gravitational force seems to be much larger than the lift force. And the inverse logic is true for the second statement. We also notice that cutting the seed slightly can increase the angular velocity, but it decreases stability. And the fourth observation is kind of connected to the third one, and this is a kind of a novel observation, is that it seems that leading edge vortices are what creates the majority of lift, and the wing root and wing tip vortices help with damping, stability, and reaching steady state quicker. So the cut seeds have this leading edge vortex, so it's why the cut seeds reach autorotation as well as the uncut seeds. But these wing root and wing tip vortices, likely due to the cutting nature or the cuts in the trailing edge of the seed, these vortices are likely much different than for an uncut seed. So this is the reasoning for why cut seeds have less stability and they just don't reach steady state as fast. So for future research, it would be interesting to expand upon previous literature. So previous literature notes that cut seeds reach autorotation reliably, but does not discuss the impact of leading edge vortices versus wingtip vortices. It would be interesting to evaluate the separate impact of these different vortices. And we could do simulations, CFD simulations, to find this out, as previous CFD simulations don't truly delve into a lot of detail on the vortex structures or their actual impact on the flight. And or we can just improve our experiment, as there are many improvements that can be made, and also to visualize the flow. So ultimately, it would be interesting to understand how the vortex structures differ for cut and uncut seeds.
Next, we'll discuss improvements for the project that could have mitigated challenges encountered during the experiment. Many of the experimental errors identified during post-processing of the data were associated with video capture, video processing, and experimental setup. The tracker software used to analyze the video data is only capable of motion tracking at the recorded FPS. So for the videos that were recorded at lower FPS, the number of data points that we were able to collect through the calibrated portion of the experimental setup were limited. And another source of potential error could have been in filming angles, which could have led to potential parallax errors. Additionally, our video resolution impacted our ability to accurately track the Maplecopter through its flight, affecting our velocity data. And finally, we had difficulty identifying a true steady state where the lift and drag forces were exactly equal to the gravitational forces, just due to the 17-foot drop height in our 1 meter section where we were collecting data. To highlight some of the video processing errors, we have a screen capture of the tracker software and some examples of the possible errors encountered during data analysis. The parallax error refers to our video capture not being perfectly parallel to the plane of motion and not in line with the video coordinate axes, which could cause length scale or calibration errors, which are highlighted on the left side. And then also the resolution error is apparent by the smudged appearance of the Maplecopter, which increased the difficulty of accurate center of mass tracking, which is highlighted on the right. Another possible error encountered for the top-down videos is displayed again with a screen capture from the tracker software. Tracking the trajectory of the seed showed a tighter radius of its gyration with respect to time, which could skew angular velocity data. And since the data processing occurs in the video plane, the software does not account for depth into the page, introducing potential errors. However, keeping these errors in mind, future experiments could mitigate the challenges we faced with data collection. Finally, we have our references, which we use to develop, research, and inspire our project. And with that, we thank you for your attention and welcome any questions.